In section 3.6, we look at a few characteristics of ionic compounds. And it's going to be important to remember how these characteristics are different from those of the molecular compounds that we'll be talking about later on. So, ionic compounds are found in what we call crystal lattices. And in a crystal lattice, you have an approximately infinite array of a repeating pattern of positive and negatively charged anions and cations. And the unique way in which the crystals are, or the ions are organized in the crystal, gives rise to the shapes and the colors of these crystals. So perhaps you can see that sodium chloride, table salt, is formed by a repeating pattern of cubes. And if we look at a macroscopic sample of sodium chloride, you'll see that indeed it's made up of cubes. And so if you're curious about this, you can go home, look at some table salt, and you'll see that the crystals are always cubic, and that reflects the shape of the unit that makes up the crystal. Crystalline compounds are often really brightly colored, especially when they involve transition metals, and good examples of these are things like rubies and other semi-precious transition metal containing ionic compounds. Now, ionic crystal lattices are very strong, and as a result, ionic compounds have very high melting points because a large amount of energy is required to break ionic bonds. In fact, an important thing to recognize is that all ionic compounds are solids at room temperature as a result of the strong bonds that are holding ionic crystal lattices together. Just by way of example, the melting point of sodium chloride, table salt, is 800 degrees Celsius, and if we compare that with a typical molecular compound such as water, we see the melting point is only 0 degrees Celsius. So in addition to high melting point, another characteristic of ionic compounds is that they are hard and brittle solids that shatter when you apply a mechanical force to them. And this little diagram that I'm about to show you next will illustrate why that is. So here we have a crystal of sodium chloride, and we can see that we have alternating positive and negative charges, and that's what's holding it together. But if I apply a mechanical force to one of the layers here, and I knock down those chlorides, you can see what happens now is that I have ions with the same charge that are adjacent, so they're going to repel one another, and my crystal is going to explode. So a typical characteristic of an ionic compound is that when you apply a mechanical force, it'll shatter, and you'll probably know that if you ever ground up some salt. In addition to very high melting point and being brittle, ionic compounds have an interesting quality that when they are dissolved in a liquid, they will conduct electricity, but in the solid state, they won't. Now, why is this? Well, electrical conductivity requires mobile charges, mobile positive and negative charges. So if I take a sample of pure distilled water, the particle that makes up distilled water is electrically neutral water molecules, and such a sample would not conduct. If I take a sample of an ionic compound, a crystalline ionic compound, the solid ionic compound, because the positive and negative ions are fixed in a solid, again, such a material would not conduct electricity. However, if I take the water and pour it into my solid ionic compound, and I dissolve my ionic compound, what happens is that the crystal separates out into individual positive and negative charges, and now I have mobile cations and anions, and I will find that I have high electrical conductivity. So, ionic compounds have the characteristic that they don't conduct in the solid state, but when they are allowed to, and when they are dissolved in a solvent such as water, they will conduct, and that's a really useful way of telling whether you have an ionic compound or not. Okay, well that concludes chapter 3 and a little bit about ionic compounds. In our next chapter, we'll be talking about other classes of compounds.